'Cause your heart isn't beating enough. I feel blue.
Hi guys, my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. Move on to the topic of kinetics. So basically, thermodynamic analysis tells us if a forward or reverse process is favored, but it doesn't tell us how fast it's going to be. And so as an example, let me show you carbon in the form of diamond going to carbon in the form of graphite, since carbon can have many different forms. The thermodynamic delta G, Gibbs free energy value, is negative 3 kilojoules. So by looking at this, we learned in the thermodynamic chapter that this reaction is spontaneous, right? Because it has a negative delta G value. But just because it's spontaneous and it happens does not necessarily mean that it's going to instantaneously happen, like spontaneously. And so this is a favorable reaction, but does it occur at 25 degrees and 1 atmosphere, which is the standard temperature and pressure? And the answer is no, it doesn't. It's a very, very slow reaction. And so the kinetics, rather than the thermodynamics, is controlling this particular reaction. So what this means is that diamond is kinetically stable with regard to graphite and also thermodynamically unstable. And so kinetic analysis talks about the speed or the rate of the reaction. And we basically use experimental techniques to observe the concentration of the reactants and products. So let's do an example here. We start out with 2NO2, which is nitrogen dioxide, and this is a gas, and it decomposes to nitric oxide, which is also a gas, and oxygen gas. And so at a temperature of 25 degrees Celsius, this reaction is happening, but then what happens if we quickly heat this to 300 degrees Celsius? What we can do is we can measure the concentration of the reactants and the products at different times. And so what we do is we plot the concentration of the reactants and products, so NO2, NO, and O2, versus time. Because as time goes on, the temperature is increasing and there's going to be a change in the concentrations. And so basically, we can write this out as reaction rate as being the change in the concentration of the reactants or products per unit of time. And we can write this out in a more mathematical way as rate is the change in the concentration over the change in time. And so since the concentration of NO2 is going to be decreasing, the change in NO2 is going to be negative, right? Since the reactants are getting used up in this reaction. And on the other hand, the delta NO and also the delta O2 over time are going to be positive since we're forming these products in this process. And we want to work with positive reaction rates because there's no such thing as a negative rate of reaction. And therefore, we write out the rate as the negative change in the reactants over time, or we can write it out as the rate of formation, which is positive for the products. So this is a very important relationship that relates the reactant concentration and the product concentration and how you want to write out the rate equation based upon whether you're dealing with the concentrations of reactants where it has to be negative here or products where it has to be positive. So now let's look at this equation again, going from NO2 to NO and O2. What this equation tells us is that as the concentration of NO2 decreases, the same ratio of the rate of NO increases. But the concentration of O2 increases half as fast, right? Because of the ratio 2 to 2 to 1. So we have to take this into consideration when we write out the rate laws. And so for this reaction, we have negative delta NO2. Remember, it's negative because it's a reactant, over dt, or delta T, is equal to the delta concentration of NO. Again, here it's positive since it's a product. But for oxygen, since it's 2 to 2 to 1, we have to put a coefficient in front of it, and it's going to be 2 delta O2 over delta T. And the reason why we put this 2 in front is because the oxygen increases half as fast since it's half the amount of the NO, for example. And this, in turn, can be written as negative 1/2 delta NO2 over delta T, which equals 1/2 delta NO over delta T, and then delta O2 over delta T. So I'm going to write this in a more general form for you guys so you can do this for any reaction. And so if you have A going to B plus C, where these small alphabets represent the coefficients and the capital letters represent the actual molecule or element, we can write out the rate as being negative 1 over A delta A over delta T, which equals 1 over B delta B over delta T, which equals 1 over C delta C over delta T. So you can actually use this equation for any reaction that you get. So for here, we considered only the forward reaction, but after the product has formed, some of it can return to the reactant. And so we need the rate of the forward reaction and the rate of the reverse reaction. And basically, it's easier to study the initial reaction when very little product is present. And so we compare initial reaction rates for different reaction, where the reaction rate only depends on the concentration of the reactants, no longer the products. And so from here, we can get the initial reaction rates for different reactions and compare them in an experimental setting. So after doing the experiments to observe the change in the reactant concentration over the change in time, one can re-express the rate in terms of a rate constant, which is given the term K. So this is the rate constant. And with regard to the concentration of the reactant. And also we have another term called N, which is the order of the reactant. So now we can rewrite the rate equation as negative 1 over A, and this is the coefficient, delta R over delta T. This is what we had before, right? And it's negative because it's with respect to the reactants. And this can now be written as the rate constant multiplied by the concentration of the reactants to the power of N, where N represents the order of the reaction. And so in the previous example, where we had NO2 going to 2NO plus O2, we can rewrite this rate as either negative 1 over 2 delta NO2 over delta T, which is what we did before. And now this can be rewritten as the rate constant multiplied by the concentration of NO2 to the power of N. And this order of the reactant is what we want to determine. And so what we use is the differential rate law. And this is the rate as a function of concentration, and we study the initial reaction rates as a function of concentration to determine the order of kinetic reactions. And so now I'll show you an example of how this is done.
Bittersweet company is what you give to me, babe. Make